Hello and welcome to this tutorial where I will show you how to make a 4 by 3 input multiplier using gate level Verilog HDL. So in this tutorial we will implement this 4 by 3 input multiplier where this is the circuit that uh, that is involved in making of this 4 by 3 input multiplier. So here, as you can see, this input has 3 bits and this other input has 4 bits. So in order to implement this circuit, uh, as you can see, we need a bunch of AND gates and 2 full adder modules. So it is important for us to first make this 4-bit adder module. Uh, uh, so So here I have already added this 4-bit adder to this module. So as you can see here, this is a 4-bit adder which I have made through 4 full adder modules, right? So in order to know more about how we can make this 4-bit adder using 4 full adder modules, uh, you need to um, you need to go through my previous tutorial on full adders. So in this tutorial, I'm assuming that you already know how to make a 4-bit uh, full adder. So let's compile this, and once we compile this, then we will. So as we see, this is there are no errors, and now let's add a new source file to this project. So select this Verilog module, write this name mult 4 by 3. So this is the name of our 4 by 3 input multiplier. So then click next, next, and finish. Right. So we want to implement this circuit, this particular circuit. So uh, so as you can see, it has 2 inputs, which um, this A and this B, and it has this output. So this output is the product. So let's call the product. Let's denote the product by P and inputs by A and B. Right. So now this input A has 3 bits, as you can see here. So A can be declared like this: a 3-bit input, and this input B, it can be declared, because it is a 4-bit input, so it can be declared like this. So we use input command, and then we specify that this input has 3 bits and this input has 4 bits, right? So, and in output, as you can see, it has 7 bits, right? So product has 7 bits. So it means whenever you are adding, or sorry, multiplying 2 numbers, so you just add the total number of bits in both numbers, and then you will know, so your product will have that many bits. So here we have a 3-bit input and a 4-bit input. So now you just add these the number of bits in this input and the number of bits in this input. So you will find out your output will have 7 bits. So you define an output with 7 bits, right? So now we first implement these AND gates, where, as you can see here, we compute the AND of all the bits in B with A0, which is the bit at location 0 in number A, right? So let's first do that. So we use this label G1, or let it be G0 to begin with, and so it is, so, so we are ANDing A0 with B0, right? So, and the output in this case, as you can see, is C0, which is the the uh, the first bit or the least significant bit in the product, which is P0, because we have defined product as P in our program. So this is going to be P0, right? Okay. So now let's implement these three operations. So in order to implement these three operations, we need to define some wires, because as we know, we have defined the inputs, or rather we have declared or defined the inputs A and B and the outputs, but outputs of these intermediate gates, we have not declared them, right? So we need to, we generally use wires to declare these outputs. So let's so let's define some wires. So we take, we take two 4-bit wires. So because we need wires for this 4-bit input and we need wires for this 4-bit input. Okay, so for clarity, this wire type is also a memory element, uh, which is generally used to assign intermediate outputs of the intermediate gates, right? So now let's implement these three AND gates, as you can see here, and G1 is the label, and then we specify output this output of this AND gate. Let this be W10. So this is the wire W1, and this is its 0th location, and so this is the output of this AND gate. And so the input of this AND gate, as you can see, are A0 and B1. A0, right? So in this case, we have A0 and with B2, and the output is going to be W1 of 1. So let's copy this one. It is convenient to copy this one and change its bit locations. So we are multiplying, sorry, we are ANDing B2 with A0, where W1, the location of this AND operation, we are going to store it in W1, 1, right? And this, let's change this label to G2. And then we have another AND gate, this one, where we are computing the AND of A0 with B3, and we store this output in W1, 2. So we store the output here, and so this is, so now we have implemented all these 4 AND gates, and so this W1 is the input of this to this 4-bit adder. So it is a 4-bit input. So we have specified first 3 bits, W10, W11, and W12, right? So we've specified all these first 3 bits. So now let's specify the final one, which is, as you can see, is 0. So let's assign a 0 to the final location of W1, so which is W1 3, and we assign a 0 by stating the number of bits in this number, binary number, which is 1, and then we stating the type, and then we state the digit, binary digit. So this is how we specify a binary digit. Okay, so now we have done this part. Now we need to implement this part, and let's use this AND gate. And so let's use this label G4, and now so when we defined this W2 and W1, we decided that this output of these AND gates are going to be stored in W1, uh, uh, and output of these 4 AND gates would be stored in W2. So now we will use W2. So here, as you can see, we are computing AND of all the bits in B with A1. So this is A1 and this is B0. Right. So now just copy and paste and repeat this multiple times, and then just change the inputs. So let it be G5, and so output of this AND gate. So this output of this AND gate is stored in W0, which W20, which is here, and so therefore the output of this AND gate would be stored in W21, right? So this would be W21, and here we keep A of A1, because we are computing AND of all the bits in B with A1. So this is going to stay A1, but this time we will compute its AND with B1, right? And next we compute its AND with, so we will keep going like this. So this is A, right, A1, this will stay the same. This is A2, and this is going to be G6. So the label must be unique for each instance of a gate command, right? So this is again G7. Let's store the output of this AND gate, where we are computing AND of A1 with B3 in W3. So right. So this is, now we have successfully implemented these two operations. Now let's add uh, these two uh, numbers, which is W1 and W2. Right. So in order to add these two numbers, we have already made this 4-bit adder. This is 4-bit adder, and so let's just use this straight away. 4-bit adder, and specify this instance G8, and now you just specify the output. So now we need to store the output of uh, this full adder in some wire type, uh, in some wire type memory elements. So therefore we need to define this wire, uh, say S, and let it be 5-bit, because output of a 4-bit binary adder is in 5 bits. So therefore we specify, or we declare this another wire type memory element. So these outputs of this first binary adder are again intermediate outputs. So, and I've already um, specified that we use wire type memory elements or register type memory elements to store these intermediate outputs. So again, we have therefore specified this wire type uh, wire type memory element S. which has 5 bits. So let's write it here, S. And so S is going to be the output, and we have two inputs, two 4-bit inputs, which is, first one is W1, which is which stores these operations individually in its individual bits, and the W2 stores these operation in its individual bits. So let it be W2. So now so once we have specified this, now we have successfully implemented this part, and now we need to implement this part. But before implementing this part, you can see that least significant bit from the output of this 4-bit adder block is part of the product. So first we need to assign this least significant bit. So let's use this assign command, where we assign that P of 1, which is the product at location 1, is equal to S of 0, which is the least significant bit in the sum of this 4-bit adder, right? So once we do that, now we just need to implement this AND operation, and then we add these outputs of these operations with the sum from the previous adder, right? So first we need to implement these AND operations. So in order to implement these operations, I just copy these 4 AND commands, and then we modify it. So first of all, let's change the labels. So let this be G9, G10, G11, and G12, right? And so now we also need to define a third wire of 4 bits, W3, because we need something to or we need a container or a memory element that can contain outputs of these operations, right? So we define this W3, which is again a 3-bit input. So we change this to W3, 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 and W3. And here, as you can see, we AND A2 with all the bits in B. So we do not change anything here. We just need to change this thing. A2, 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 and A2. So this particular operation now performs AND of the most significant bit in A with all the bits in B, and stores the AND operations, the output of these AND operations in W3 in this order, where, as you can see, W0 contains the AND of A2 and B0, W3 1 contains A2 AND of A2 and B1, and so on, right? So now once we have this W3, now we can just add these two 4-bit numbers using 4-bit adder. So we use this G13 as this label or instance, and so the output of this, so let's first specify the inputs. So, and then we will see what are going to be the outputs. So one of these inputs are W3. So let's first specify this W3, which is a 4-bit number, which we came up with from here, and this is again a 4-bit number which does not involve the 0th bit in the sum of the previous addition, right? So this means we can ignore the 0th bit or the bit at the 0th location and take the final 4 bits. So this is how we do that. We specify the location of these upcoming bits, and we say that we do not, and we, as you can see, we ignore the zeroth location. So this means the sum at location 0 will not be added, right? So so now uh, let's specify the output. So as you can see, output of this final adder are actually bits of the final product, right? So these are this is the sec the product bit of the product at location 2. This is the bit of the product at location 3, and so on. So let's specify that. So we here in our code we specify product by P. So instead of C, here we use P. So let's specify the location. So we say that store the output of this sum in location 6 to 2, which is exactly given here, right? So now we are ready to run this to compile this module. So this is complete. Let's save this first and then run its behavioral check. And as you can see, it is perfectly fine. There are no errors. So let's uh, make it test bench. So select this Verilog test fixture. Add let's call it TB. So we specify TB underscore before the name of the module. So the name of the module is mult 4 by 3, right? So let's just click next and then click this module mult 4 by 3 to link with this test bench, right? So let's and click next, click finish. Okay, so here it has already declared the inputs and output, and it has also uh, specified the call to the module. So here you just need to specify the four input. So in fact, A is 3 input number, so let's specify the three bit number. So let it be say 101, and this is a 4-bit input. So let it be 1101. So now we want to multiply these two numbers and see its output. So let's save this and now run its behavioral check, and it seems it's perfectly fine. There are no errors. So let's click on this simulate behavioral model and see whether it is working fine or not. So apparently there are some errors. So let's see what is the error. So apparently the issue is in the definition or declaration of these wires W1, W2, and W3. So the mistake that we might have made are the number of bits. I guess we only specified 3 number of bits instead of 4. So let's see whether this is true or not. Yes, I think we did make a mistake. We should have specified it to 3 colon 0, because this way now we are specifying 4 bits. So now so once we have corrected this mistake, let's save this. Let's see whether uh, there are errors. So there are no errors. So let's compile the test bench now. So click rerun, and now click on the simulate behavioral model. So it says that there is a simulation open already. So let's close the previous simulation, and now you need to right click and rerun all. Okay, so I hope this is, yeah, so it's working perfectly now. So so when you multiply these two numbers, that is 1101 with 101, you get this answer, that is 5 zeros and then 1, so which is exactly what it should be. So that's it from this tutorial. So I'll be back with some exciting tutorials on Verilog implementation of various digital logic design circuits.